we're looking at laws of indices. So we'll first look at what we mean by indices. We'll focus on the 5 main power rules, and then we'll finish off with a couple of exam style questions. So indices is just the plural of index, and index is just another word for power. So this could be laws of indices or laws of powers. They are interchangeable. So what do we mean by powers? Well, just to make sure we're all on the same page, if I have, say, 3 to the power of 4, all that means is we've got 4 3s all in a long line timesing each other together. So that would be 3 to the 4. Likewise, if we had, say, 7 to the 5, all this means is we've got 5 7s all in a long line timesing each other together. So that's what our powers represent. Let's look at our first power rule now. So might move this over slightly to give myself some more space. There we go. So x to the a times x to the b. Well, we talk about x, to keep things general. So it's some number to some power times that same number to some other power. Let's do an example. Let's say we've got 8 to the power of 3 times 8 to the power of 4. Well, all we're doing here is, let's kind of draw this out and see where we're at. So we know 8 to the 3, or 8 cubed, is just 3 8s all in a long line timesing each other together. And 8 to the 4 is just 4 8s in a long line timesing each other together. 8 times 8 times 8 times 8. And we're timesing these two things together. Well, all we're left with is a much longer line of 8s timesing each other together, right? So in this case, we've got 7 8s timesing each other together. So we can rewrite this, kind of working backwards, we can rewrite this as 8 to the power of 7, right? This tells us we've got 7 8s all in a long line timesing each other together. And so in general, our power rule can be x to the a times x to the b is equal to, well, what have we done here, right? We've just added up all the 8s that we've got, right? We've got 3 8s here, and we've got 4 8s here. We've added them up to get 7 8s, and this is 8 to the 7. So in general, all we're doing is we're just adding up all of the, in this case, to keep it general, we've got all the x's, right? We're just adding up these two numbers together to get our new power. So that's our first power rule. Our second power rule, x to the a divided by x to the b. So let's keep these same numbers, right? Let's say we've got 8 to the 4. Actually, I'll do 8 to the 5, make it more interesting. 8 to the 5 divided by 8 to the 3. Well, I'm actually going to rewrite this as a fraction, right? We'll say this is 8 to the 5 over 8 to the 3, or 8 cubed. And if I was to write this out, if I was to write this out to actually see what's going on here, well, 8 to the 5 tells me I've got 5 8s in a long line timesing each other together, and 8 to the 3 tells me I've got 3 8s in a long line timesing each other together. Well, we can see we've got a common factor of 8, right? I could, whenever I've got a common factor, I can cancel it out from the top and the bottom. And likewise, again, I've got a common factor of 8 on the top and the bottom. And again, I've got a common factor of 8 on the top and the bottom. And so because we basically cancel as many 8s as we're dividing by, in this case, we're dividing by 8 times itself 3 times. And so we cancel out 3 8s. We're basically, knocking these off of our numerator. And so rather than 8 to the 5, or, rather than 5 8s timesing each other together, we're left with just 2 8s timesing each other together. And so our new power, in this case, would be 8 to the power of 2, right? So in general, if we've got some number to some power, and we divide that to the same number to some other power, because we end up cancelling the number of 8s, in this case, that we're dividing by, we basically just end up subtracting them from our numerator, right? We subtract them from this 8 to the 5. So we end up just doing a very standard subtraction of powers. Let's look at, so that's our second power rule. Let's look at our third power rule. So this is x to the a all to the power of b. So in this case, we know anything to some power. Let's do another example. Let's say we've got 8 squared to the power of 2, to the power of 3, let's say. Well, we know 8 squared in this case is just 8 times 8. and we're doing this to the power of 3. Well, the power of 3 tells us we have 3 of these brackets in a long line timesing each other together. And so in this case, I've got 3 of these brackets in a long line, and they're all timesing each other together. There we go. Well, if we look at this, I don't really need these brackets anymore. I could rewrite this as just 8 times 8 times 8 times 8 times 8 times 8. Well, let's take a step back and see where we're at, right? So in this case, this 2 tells us that we've got 8 times 8 in our brackets. It tells us we've got 2 8s per bracket, right? We've got 2 8s here, and we've got 2 8s here as well. The 3 tells us how many brackets we've got, right? The 3 tells us we need to take our bracket and times it by itself 3 times. So this 3 tells us we've got 3 brackets. And so if we wanted to work out how many 8s we've got in total, without actually counting up all of our 8s, we just take the number of 8s per bracket and we times it by the number of brackets. In this case, all we're doing is, we're taking the number of 8s per bracket, which is 2. So it's going to be 8 to the 2, and we're timesing this by the number of brackets. So the final power is going to be 2 times 3, which in this case is 8 to the 6. We can check that here as well. We've got how many 8s? We've got 1, 2, 3, 4, 5, 6 8s, all in a long line, timesing each other together, which again is 8 to the 6. And so in general, our power rule is going to be anything to some power, to some other power. What we do here is we times the powers together, right? We times those powers together. And that allows us to calculate how many x's there are in a long line timesing each other together. So that is our third power rule. Our fourth power rule, try and fit it all in. Our fourth power rule, x to the minus a. Well, it takes a bit of a stretch to the imagination to start off with understanding this, but we'll see how we go. So stay with me for 30 seconds. Let's say I've got 8 to the 5 divided by 8 to the 3. Well, in this case, we know from our previous power rule that we just subtract the 2 powers, right? So I end up with 8 to the 5 minus 3, which is 8 to the 2. And I could rewrite this as well in a slightly different way. Rather than dividing by 8 cubed, or 8 to the 3, I can times by 1 over 8 to the 3. And this isn't any different from, what you're used to before. We could think of this as a nice little example. We can do, say, 20 divided by 4, and we get 5. Or we can think of this as 20 times 1 over 4. And again, we get 5. So that's all I'm doing here. I'm just rewriting this in a slightly different way. And we can also see what we get if we do, for example, 8 to the 5 times 8 to the minus 3. Well, we know from our first power rule that when we times these two things together, we add the powers. And so we end up with 5 plus minus 3 in our new power, which gives us 8 to the 2. Well, if we look at where we're at now, we've started off with 8 to the 5 in both cases, and we've ended up with 8 to the power of 2 in both cases, or 8 squared. So what we can see is the middle things that we're timesing by, these two things must be the exact same, right? They must be the same thing. There's no way these could be different things. And so, I can say I know that 8 to the minus 3 is the exact same as 1 over 8 to the 3. And all this minus is telling us to do is 1 over, basically. So in general, we can say x to the minus a is just equal to 1 over x to the a. That's our fourth power rule. Our final power rule is x to the 1 over a. If we explore what that means, we can do, again, stay with me for a second. Let's say we've got the square root of x all squared. Well, I know if I square the square root, I get back to the original number, right? The square root of 9 is 3. If I square that, I get back to 9. And so that just gives me x. Likewise, if I again, stay with me for a second, if I do, say, x to the half to the power of 2, well, I know from my third power rule that I times those two numbers together, right? So I times those two numbers together, I get half times 2, which again gives me x to the 1, which is just x. And so what we can see, right, if we've ended up with the same number, the same thing in both cases, we've got x in both cases, and we started with root x here and x to the half here, and we squared them both, well, these two things must be the same thing again. I know that x to the half must be the exact same as the square root of x. And I might write this properly as to put a little 2 there. It's the square root of x. And in general, I know that anything to the 1 over a is just going to be equal to the 8th root of that thing. So that's our 5th and final power rule. Let's look at a couple of examples now. So let's look at a past paper question. So this is going to test our multiplying and dividing. We've got 3 to the 4 times 3 to the 5, and we're dividing it by 3 to the 2. Well, timesing, I add the powers together, so I get 3 to the 9 on top, and dividing, I subtract the powers, so I end up with 3 to the 7. 3 to the minus 3, well, I know that minus is just means 1 over, right? So 3 to the minus 3 just means 1 over 3 to the 3. 3 cubed is 27, so I get 1 over 27. Finally, 64 to the 2 over 3. I'm going to be slightly smart about this. I'm going to make this slightly easier and split it into 2 bite-sized chunks. This is like 64 to the third times 2, right? A third times 2 is just 2 over 3, 2/3. I know that from my previous power rule, when I've got something that looks like this, I can work backwards, right? If I've got a times b in my power, I can write this as x to the a all to the power of b. And so in this case, I can rewrite this as 64 to the third all to the power of 2. Well, 64 to the third, I know my my cube numbers, so I know that's going to be 4. 4 times 4 times 4 is 64. The power of 2 gives me 16. And so that is the end of our power rules, or the laws of indices, as it's otherwise known.